Hello and welcome to another exciting session for ENGR 330 Fluid Mechanics, recitation on Chapter 5. This chapter is kind of long, so we still have to look at some more problem solving skills for the linear momentum type of problems, controlled volume type of problems. So let's explore some more concepts we learned in class and then look at some problems to apply this material we learned and then see if we can solve some engineering problems. Okay, let's look at a problem. We're asked to determine the magnitude of the horizontal component of anchoring force required to hold in place the sluice gate as shown. Okay, and we're asked to compare this with the size of the horizontal component of the anchoring force required to hold in place the sluice gate when it is closed and the depth of the water upstream is 10 feet. Okay, and if you remember, if I were to close this sluice gate, right, it should ring a bell. All of this water is not going anywhere. It's this whole head is being held by this gate, and then it should be the type of problem we solved in chapter 2 where we talked about hydrostatic forces. So if you draw a free body diagram for the gate, it would be the reaction force at the gate and the hydrostatic force acting on the gate. So from there you can compute the reaction force, okay, or the horizontal component of the anchoring force, I should say. And if you did the preparation for the quiz, if you looked at all the problems, there are examples which are similar to this. Maybe the example was more in terms of just variables, not exactly these numbers, but it kind of gives you the idea. But again, this is a good problem which kind of ties what we learned in chapter 2 and what we learn now. And then also, before we go ahead and start the problem, let's think about this. So if this was closed, you would anticipate that the force required to hold it in place would be more because there is no flow going out. Whereas if I open this gate now, this head of water is going in this direction, right? So that would mean that I won't need as much force to hold this head of water now when it is open. Okay, let's check and see if what we think is what we get, and I think we should get, when it is closed, a higher reaction anchoring force. When it is open, it will be lower. Okay, let's try to prove our ideas here. Okay, so in the first case, let's quickly solve the problem when the sluice gate is closed. Okay, so if it is closed, then I would have the gate here and this gate, and there is no flow here. Okay, so that would mean I need to come up with a, if you look at this as your control volume, okay, look at this control volume, there's no flow going out, so it's pretty steady here. So you can then compute the hydrostatic force on a plane surface. If you remember it, it is F equals gamma specific weight, here in this case for water, height of the centroid measured from the free surface times the area. Okay, and for this problem, since we are not given a width of the sluice gate here, let's say it is some b. Okay, so this is your width dimension, let's say it's some b, and then we'll divide our answers with b so that we get these forces per unit length. Okay, all right, so if you were to do that, then this is a simple calculation. Then if you want to draw the free body diagram, and by now I'm sure you're pretty confident doing that, then F will be same as R in the X direction if I say this is my X. Okay, so if you compute F, it will be equal to Rx. So let's go ahead and do that. So Rx, which is nothing but F, will be gamma. Height of the centroid in this case is this 10 feet. Okay, so O over 2 will be your height of the centroid. So 10 over 2 and the area will be the height, which is 10 times B, which is your depth, into the board here, or into the screen here I should say. Okay, so if you put in the numbers and if you divide Rx with B, you should get, and then if you use the correct units, it's feet, so use gamma here from your British units in pound per cubic feet. So you should end up with Rx over B as 3120 pound per feet. Okay, so that's the second part of the problem, but since it was easier to do it, we just did that. And for the first part of the problem, when the sluice gate is open, let me erase this. So now our control volume would be slightly different. So it would be encompassing this guy here. Okay, this is how our control volume now would look like, right? And then by now, if you remember, if you want to compute a reaction or the anchoring force in the x direction, and then if I neglect friction for this problem, which happens here, right here, this frictional force, if you consider that to be negligible, then there would be hydrostatic force here, there would be the hydrostatic force here for this height here, and you have a velocity coming in, and you have a velocity going out, and then conservation of mass principle says this flow rate here should be equal to this flow rate. Okay, so we can try to write the conservation of linear momentum in the x direction, and then it will happen that our only unknown would then be the anchoring force, which would be Rx. Okay, so let's go ahead and do that. So if I name this guy as section 1, this guy as section 2, then I'm sure by now, if you listen to my previous recitation, by now you know how you can compute the various quantities. So at section 1, the momentum will be that, and h I refer to as the 10 feet. Okay, and then at section 2, it will be rho u2 squared times h, where h refers to the small height here, which is 1.5 feet at section 2. Okay, and this is similar to the convention used in the example. You know, instead of putting numbers directly here, let's look at the formulation. It should be equal to the hydrostatic force at section 1 minus, just a convention based on the coordinate system, this would be the hydrostatic force there, minus Rx. Okay, so you have those numbers, and then if you look at this problem, the only unknown in this case is Rx, okay, and you can always convert the velocity u2, which we don't know at this point, but you know that u1 a1 is u2 a2, and you can come up with a relation for u1 and u2, right? So if you do that, you get u2 is u1 h over h, and then you know u1, which is 4 feet per second. So you have everything in the problem which is known except Rx. So if you go ahead and compute, Rx will be 1290 pound per feet. Okay, so you can see based on the previous answer, it's considerably less, almost less than 50%, right? So that would mean that it takes considerably less force to have the sluice gate in place when it is opened because there is some mass flow rate out of the system or out of the control volume. Okay, so this is nice little example of an application of chapter 2 principles and what we learned in this chapter. Okay, let's look at another example. Again, I encourage you to actually put in the numbers in the previous example, since it saves a lot of time for me not to go through the calculations, and I assume you're very good with calculators, so make sure you check the answers and make sure you understand how we develop the formulation. Let's look at another problem. You're given the results of a wind tunnel test to determine the drag on a body are summarized below. The upstream, which is this section 1, is uniform, the velocity is uniform at 100 feet per second, and the static pressures at P1 and P2 are 14.7 psia, pounds per square inch absolute. The downstream velocity distribution, which is symmetrical about the center line, so you can see that it's symmetrical, and it's given by these profiles where u is the velocity in feet per second, y is the distance on either side of the center line, so y goes this way. Okay, you're asked to assume that the body shape does not change normal to the paper, so if you look anywhere across this into the screen, the body is still or has the same shape. You're asked to calculate the drag force, that is the reaction force in x direction, exerted on the air by the body per unit length normal to the plane of the sketch. Okay, since we don't know really the depth of the body, we are asked to compute it per unit length. Okay, again, we need to come up with a control volume description to compute the force, which would be an external force acting on the control volume. Okay, so if I were to pick a control volume, I would probably go from here to all the way where there is change in these velocities. Okay, and everywhere else it's pretty constant. Okay, but we really don't know this height h, but something which we can actually compute. Let's go ahead and apply the conservation of linear momentum in the x direction. This is your positive x, this is your y. Okay, if you go ahead and apply that, you get minus rho u1 squared 1. Again, I won't go into details of how I got this because previous recitation we pretty much hammered this. So I think you know why this is. Just briefly, u is going this way, so v dot n will be opposite direction, so that's why you end up with a negative sign. Whereas for this guy it's a little bit tricky, so you have to remember your math. If you look at this function, this is an even function, right? So an even function is defined as f of x is f of negative x. So your integral will be 2 times 0 to 3 if this is my center line, this 0 to 3, so plus 2 times 0 to 3 feet u rho u dy and will be equal to minus rx, which is what we are after. Okay, so in this case we have to come up with this area here, and in this case for section 1 we know that it's unit depth, whereas we don't know this dimension. Let's call it some h. Okay, um, so at this point we have two unknowns. We have Rx and H in the problem, which are two unknowns, but then again our conservation of mass helps us. Whatever is coming in through section 1 should go out at section 2, so that should help us evaluate what would be H. Okay, so if you apply the conservation of mass from between section 1 and 2, you get rho H u1, okay, which is rho u h in this case will be equal to 2 times integral 0 to 3 rho u dy. Okay, so you can go ahead and compute h from here. You know u1, you know the profile, and it's pretty simple integral. You can compute that, and then you'll get h to be 5.1 feet. And if you look at the figure, it makes sense. The whole length is about 6 feet, so it should be less than that. Okay, so it's about 5.1 feet. So once you know this, then the only unknown in this case would be Rx. Everything else you can evaluate it. Rho is for air. Okay, you can look up from the table. Make sure you pick the correct units, so it will be slugs per cubic feet, whatever is the value you get from the table. I think it's 0.0024 slugs per cubic feet. So if you put in the numbers and solve it, you should get Rx to be about 17 pound per feet into the screen, okay, or into the board, I should say. So 17 pounds per feet. Okay, so the key thing here was to see that you need to come up with some length scale here, whereas your conservation of mass can help you get that length scale. Other than that, it's pretty straightforward in terms of computing your actual conservation of linear momentum in the x direction. Okay, so this is your answer. Now let's look at another interesting problem. So consider unsteady flow in the constant diameter horizontal pipe shown in the figure. The velocity is uniform throughout the entire pipe. Okay, throughout the entire pipe, the velocity is uniform. That means you cut across any cross section, it is the same velocity. But it is a function of time, okay, which we haven't done in a lot of problems till now. So it's not that difficult, but it's given in this form u of t. Use the x component of the unsteady momentum equation to determine the pressure difference P1 minus P2 and discuss how this is related to your Newton's second law, force equals mass times acceleration in the x direction. Okay. Okay, so first we need to see what is our unsteady law. Okay, it's similar to what we have been doing when we talked about the steady flows and applying the linear conservation of momentum equal to the sum of the external forces acting on the system, except that now the velocity is a function of changing with time as well, so we need to include the unsteady term. Okay, and the unsteady term would be d over dou t of the control volume rho u the volume, and then you know of the other term, which is the rho u v dot n dA will be equal to sum of external forces, right? In this case we need to convert these pressures into forces. Okay, so at this point this is the unsteady momentum equation in the x direction. Okay, so let's go ahead and substitute what we are given in the problem and then see if we can come up with the expression which we can relate to F equals ma. So here your u is u of t, it's in the I direction, which is in the x direction. Let's go to the next page. Okay, so dou over dou t of, we have a rho u and it's function of t, so I'm going to put it inside, and if you look at it, this is dv, we can integrate it, it's just the area times another length scale, cross sectional area is pi d square over 4 times the length L, which we are given in the problem, so pi over 4 d square L, so that's the unsteady term, right? And minus, at section 1 you can write the conservation of the linear momentum would be a negative quantity, and you know why that is, since the normal is outside, it's going in the opposite direction compared to the velocity at section 1, plus rho u2 square a2 will be equal to P1 times A1, that gives us the force P2 times A2. Okay, so at this point let's see if we can cancel any terms. So if you look at it, the flow rate will be the same, right, going across the pipe. Okay, and U1 will be equal to U2. That means A1 is A2, which is true in this case, it's a no-brainer since it's the same pipe, there is nothing changing in the x direction for the pipe dimension, so these two guys cancel each other, so all we got is this and the forces here. Okay, so if you look at this, if I rewrite these terms and identify some constants here, rho is a constant, rho pi over 4 d square L du dt, dou u dou t I should say, equals, the area is again a constant, okay, pi d square over 4. Okay, okay, at this point you can see that the dimensions of this guy would be the dimensions of mass, right, kg per meter cube times the volume meter cube, so kg, dou u dou t, you know, is acceleration, right, and pressure times area is a force, and to do that, that's exactly what we are asked to relate, and that's what we get. However, in this problem we are asked to write the what is P1 minus P2. You can go ahead and cancel some common terms here. So P1 minus P2 will be rho L du dt, dou u dou t. Okay, so this is a nice little problem where u is a function of time and it's an unsteady problem. Okay, but there is nice analogy to your Newton's second law here. Force equals mass times acceleration. Okay, now let's look at some more problems. So if you remember, towards the end of the chapter, we talked about the energy equation, and let's look at some problems where we have to apply the energy equation. So you're given the hydrostatic turbine shown in figure here passes 8 million gallon per minute across a head of 600 feet, and you're asked to find out what is the maximum amount of power output possible and why will the actual amount be less. Okay, so that's what you're asked to find in this problem. Again, if you remember, when we solved these type of problems, when we did Bernoulli problems, in this case we can't do that, but there are some losses here. We identify some points on the in the flow field. So let me identify 1 and 2, and let's write the energy equation between 1 and 2, and then try to compute what we are asked in the problem. Okay, all right, so if you go ahead and write the energy equation, P1 over the specific weight plus Z1 plus V1 square over 2G plus the head minus the loss will be equal to P2 over specific weight plus Z2 plus V2 square over 2G. Okay, so in this case P1 and P2 are zero gauge. Okay, and for a large reservoir we know that V1 is zero. It's a very slow changing thing, right? So your only um, unknown at this point would be, in a way, you have several unknowns here, but let's try to come up with the maximum amount of power output possible, right, which will be based on your head, uh, HS. So HS would be Z2 minus Z1 plus HL plus V2 square over 2G. Okay, so if you want maximum power, you don't want to have any losses, right? So HL will be 0, then you know Z2 minus Z1, right, which is Z2 minus Z1, so this is a negative number, so negative 600 feet plus V2 square over 2G. You can compute V2, or in this case, since we want to have maximum uh, power, another way to look at it is, if you don't want losses, there should be negligible velocity at 2, or there should not be any kinetic energy associated with the flow. And one way to think about it is, if you have a large enough pipe here or large enough outlet, then you won't have huge losses, right? So essentially we are almost neglecting this as well. Okay, and so now let's go ahead and compute the maximum amount of power output, which in this case is W dot for the turbine would be specific weight times the flow rate times the, this is your HS, right? Z2 minus Z1. In this case, Z2 minus Z1 is negative, as we talked about, and the reason it will be negative, uh, your W dot turbine will be negative is your power is going out, so the convention minus sign is basically associated with that. Okay, and if you make sure about the units and convert this 8 million gallons per minute to cubic feet um, uh, into cubic feet per second, right? And if you want to convert everything to a horsepower, which is generally the unit we use for these powers, so you get about 1.2 into 10 to the 6 horsepowers. Okay, and you're asked to comment on why the actual amount will be less, and you can think of, you'll have some frictional losses, and you'll have some velocity here, so there will be some kinetic energy associated at this at x at exit 2, so you can say that theoretically it won't be this much power, or in practice this won't be uh, high enough power we will probably get. Okay, so now let's do one last problem in this chapter. Okay, so you're given water is pumped from a tank as shown in this figure. The head loss is known to be, which is HL. In the previous case it was 0. In this case we are given that, and where V is the average velocity in the pipe. According to the pump manufacturer, the relationship between the pump head and the flow rate is given. So this is your HS. So HP is 20 minus 20,000 or 2000 Q square, where HP is in meters and Q is in meter cube per second. We're asked to determine the flow rate Q. Okay. Again, we can try to do this by trying to represent a control volume. If I can do this just around the system, and then take this as 1, take this as 2, which we have done before, right? So we want to compute the flow rate. So let's try to write the energy equation between 1 and 2. So if I do that, it would be P1 over gamma plus V1 square over 2G plus Z1 plus HS or HP, which is the same. Okay, so let me go ahead and write HP here minus HL, right? And let's see, you need to write the other side of the equation. And then similarly at 2 would be P2 over gamma plus V2 square over 2G plus Z2. Okay, so at this point let's see what are the things we can neglect. So P1, P2, same idea, they're exposed to the atmosphere, zero gauge, right? V1, 0, large tank, and we know HP, we know HL, right? And you can try to write V2 in terms of the flow rate. right? Because Q will be B2 A2. So since you're given the diameter at this section, you can compute A2. So you can write everything in terms of Q. So you'll end up with one equation and one unknown, which will be Q in this case. Okay. So if you put uh, simplify the previous guy, so Z1 plus HP minus 1.2 V2 square over 2G equals V2 square over 2G, right? So if I do the math, Z, okay, we are online again. So what I was saying was I was trying to simplify this. So Z1 plus 20, um, and then if I simplify this, Q square 2000 plus 2.2. I'm going to add these guys and then try to represent V2 square. I took out Q square here. So 4, not in this case, 2 times G times A square. Okay, so that's what I end up here. And then if you do a little bit of algebra here, Z1 is 6 meters, so 26. So Q will be equal to square root of 26 over 2000 plus 2.2 over 2 times 9.81 times pi square over 16.07 raised to the power 4. Okay, if you do all of that and punch in the numbers, you should get 0.05 cubic meter per second. Okay, so that's your flow rate. So here in this case, all you did was wrote the energy equation between 1 and 2, and then wrote the whole equation in terms of one variable, because essentially we have one equation, right? So the whole equation we transformed into one variable, which we could do that because we knew HP is a function of Q square, so that helped us, right? And then using V2 from the fact that Q is V2A2, that helped us get that out of the way, and then I write everything in terms of Q, and then Q happened to be the only unknown, and then that's why we ended up with this answer. Okay, so this concludes the session for chapter 5. I hope you really enjoyed this chapter, and looking forward to talking to you again with the next recitation.